streaming right now?
It's just going to the YouTube channel.
Oh, okay.
It's not public. Yeah.
What time is it? Should I mic him up now?
Yeah. It's 12.
Oh, yeah. All right. If you could just attach that to your panel.
See, yeah, we'll probably put it over here because I think I'll have my head going to the right. Okay.
Sorry. It's kind of a MacGyver clip.
You got it.
Can you speak into that a little bit?
Yeah, how's this?
All right.
Can you
Yeah, that sounds
of
good.
course, I was facing sideways. Let me try straight ahead. Is that still okay?
Yeah.
All right, and I'll speak up during the. Okay. All right. I know you need what you need for filming. Will we possibly be taking the lights down just partial level during the talk? Because I think the slides are going to show up better.
Yeah, how low do you want it?
Not super low, maybe one level down. The slides will look a little better. But
Are
I
you
don't want to
talking
mess
about
with
the
it.
lighting
In the room.
Yeah.
Is it? I mean, you probably do that as a normal course, but. Probably the other way around, if we can take down that front row and leave some up in the back. It's that fluorescent bar right over the screen that's, I don't want to complicate your life. Okay. I think but now we could have some room lights on. There, okay, there. Good.
Technology, I'm old enough to remember when you would come with transparencies.
Oh, yeah.
Handwritten transparencies.
Man, I've occasionally pulled out some old ones, and do I get grief from the students now when they see that? So I quit that.
There were certain things that were really easy to do with those. Like if you wanted to show like two things moving relative to each other, like you want to say, well, this curve can be split on a long scale.
Yeah,
You
we
just
had
add
all these
one thing
things
on transparency,
worked out.
another, and you just, now it's like 2 hours on PowerPoint trying to figure out how to animate it, and it's like just slide the things
Just use like a dry erase marker and just write on it.
Richard,
Yeah,
will it be a problem for my
And there was a whole artistry of like editing.
No, this is fine.
Take like a little bit
Yeah.
of alcohol and a
Yeah,
tissue paper
this is
and
fine.
just like back down to something else. So I was talking about the medical project we had in the 90s. That was kind of like the transition period because I remember probably in about 97 getting a presentation to a bunch of doctors, and I had my data printed out on my transparencies, and I had handwritten, communicate that note to them. Afterwards, one of the doctors who invited me said, well, it's very interesting. Let me give you advice. Never talk to doctors again with handwritten slides. They assume it's going to be slick.
Okay.
It's difference of culture at that time. Now everybody has PowerPoint, right?
Right,
At that time, they were kind of offended that I would present handwritten slides.
you don't respect them enough.
Yeah, that's right. Yeah. But you always have the March meeting that tells, like, who worked for industry and who was academic, because people from industry always had a room full of people whose lives were to produce slides. Like the graphic department or whatever, they would have like slides in a camera, that they would present really slick. So why don't we go ahead and get started? This is Richard Williams from Wake Forest University, and long-standing exciton optics person, so for those of you who do excitons, you'll hear a lot of connections here. And I'm fascinated by the connections of particle physics. So go ahead and
Okay.
you have a laser
Yeah,
pointer or something
I
like
do.
that?
I do. And so thank you, David, for the invitation. It's my first time here at your university, not in the city, but here, and very nice. And anyway, for a couple of years now, we're connected in the ACC. Anyhow, so that's one thing. And yeah, the topic for today is a little more applied, maybe, than what some of you at least are doing in the Quantum Physics Institute, along the lines, though, following up on what David said. For a long time, I was certainly on the fundamental part of condensed matter physics, working on something called self-trapped excitons, a variety of them that we'll talk about. And it turned out that was useful and interesting for this scintillator radiation detection area. And so a friend of mine at Livermore, on kind of observing this, said, if you keep doing something long enough, the application will find you. So this is sort of the case. But David, so here's the experimental lab, so it's a more or less standard ultrafast lab. And again, excitons over many years were what we were working on. And then this is in their sort of representative. This is not, I'm going to show you a real detector in the next slide, but anyway, this is part of what Livermore and Berkeley used to do their version, so it's trying to do a connection here, and I'll come back to that a little bit. But, you know, who's interested in scintillators and what is left to do even in scintillator development and engineering that might interest people? So I'll go back just a few years in history. This, I guess, went into history in 2012 with the Higgs boson. So anyway, you guys know. But, so the Higgs discovery was made on the two big detectors on LHC, this CMS detector and the Atlas detector. And both of them contain essentially this object which is in green. That's the electromagnetic calorimeter. And its job is to tell where and what energy each gamma ray in the shower that comes out has. So to log the total energy of the gamma ray and to log its line of flight. And anyway, that's a crucial part of the detection. And so a little bit of it's some historical statements there, and some of you are probably going to know that better, parts of that better than I do. But that was the kind of the first time that the field came around and found the fact that I was working on self-trapped excitons, because Paul Lecoq, who's the head of the electromagnetic calorimeter project on the CMS, was looking, he was forced to look for a brand new scintillator. And again, scintillators, spectroscopic scintillators, just to define, light up when they stop. Of course, through electromagnetic interactions, you stop a gamma ray fully within the crystal, and it makes a lot of electron hole pairs, and they wind up giving light. And you count the photons of light that come off, and you hope you can interpret that as proportional to the energy of the gamma ray. And of course that gets back to the first slide, this funny word that you probably never come across, non-proportionality. So you hope it's proportional, and you do a lot better if it's proportional, but it's not. So what do we do? Anyway, so in 1990, that's when he was handed the challenge of let's do this, because we're going to go on a search for the Higgs boson in about 22 years. Anyway, find it in 22 years. And why so early? Because from 1949, and in the 1940s, there was an extremely good scintillator, extremely good, what does that mean? In those days, a very adequate scintillator, sodium iodide thallium. Kind of everybody in the field knows about that. And it's got pretty good light yield, and it's sort of decent energy resolution, but it's slow. It's microseconds, even tens of it has a tail on it, it can be tens of microseconds, and that was deadly. That was perfectly fine for, I think, most of the nuclear physics anybody was doing for those 50 years up till then. But people designing this LHC knew that they were going to be having to look at like one successful event in 10 to the 12, something like that.
So what controlled that lifetime? Was it just a recombination time of the electrical pairs? Or?
It's, and we'll get into that. It's that to make it work well, you loaded it up with the thallium, and the thallium, and it wasn't known all of this until some of what I'll show you. The thallium is an extremely good, strong trap for both signs of carriers. It traps electrons and holes, and it does so at the doping levels that are used with a trapping time of 3 picoseconds or less. So it grabs them in a hurry. It prevents excitons from being formed, for example. So that's a good question. I jumped ahead, but I like to do that. And in fact, so what's going to go into this is such as how do we measure those capture rates and things and compare their excitons. The other thing that goes on to it is concepts that when you make these electrons and holes, especially the electrons, you just made them with maybe a megavolt Compton scatter or megavolt, the big M, and so they're really high energy. Well, they'll lose a lot of that energy very quickly, femtoseconds, even sub-femtoseconds, until they get down to one band gap above the conduction band minimum, and then you can't make any more electron hole pairs by collision, so you got to emit phonons. And what that means, you got hot electrons with up to, these are typically 6, 7, 8, 9 volt band gaps, so you got like up to 9 volt hot electrons, and that's really hot in KT. So, and what this is good. It's invested time. It'll save time later. So, and then on self-trapping, my favorite word that I mentioned. So the holes stop immediately when produced. This, by the way, what I'm doing here is nanoscience on the picosecond scale. I'll show you what a track looks like, an electron track, and it's about 3 nanometers in radius, the initial deposition, and it's about a micron long for high energy electrons. So that, you can't get much nanowire-ish than that. Huge gradient driving diffusion, except for the hot electrons. They have so much energy, tens of thousands of degrees. Anyway, they don't care that they're building up a huge electric field. They do not feel the electric field, so they go rushing out, leaving behind a positive line charge of the self-trapped holes, and they build in just an enormous electric field, and then as soon as they thermalize, you get into the physics of that. So it's, these are the things we're talking about. Thank you for that. I need to watch this and see, but this one's interesting. So let me go a little bit more with it. Just so the job was you had to come to something that could do 10 to the 8 collisions per second. So it's got to recover in 10 nanoseconds, and it's not even if you well, you do have that, and you still have problems because then you've got the statistics on that. You're going to have some fall on top of the neighbor and so forth. So. But anyway, that's that kind of limit, and remind me to come back to that before we go off this slide. So it was a totally new thing. There really were not any scintillators that had that kind of speed and had what else you need, which is great radiation damage resistance. And so it was to launch out and to say there. And so when I was at CERN in 1992 with Paul, when he had to make that decision. And there were 2 materials that had come up through the pipelines, and one had only been discovered and shown to be a scintillator 2 years prior in Russia, and that was lead tungstate. And it's the only reason it's fast enough is because it's almost thermally quenched. So you get a tiny little bit of the light, but it's fast because of the thermal quenching. It has measurable sensitivity, but you don't need that when you've got huge gamma rays coming in. And then the other one was a Western invention, cerium-doped lanthanum fluoride. That has to be grown in an overpressure of fluorine gas. Anyway, so it's based, it's really high tech. And what are you going to have to grow? So this green, that looks simple enough. It's a little green shell there. That contains 68,000 individual crystals, single crystals about this long and about that big. And you probably could carve 4 of those crystals from one boule, but there's such a high selection going on to discard the defective ones and so forth. You sort of count, it's going to be 1 week of high temperature furnace time to produce every single crystal. So that's 68,000 furnace weeks to go. And so the Soviet Union, which was falling just at that time, had a big program to make laser crystals, and this was an oxide just like that. So that's one thing Paul had going for, and also our government, everybody wanted to employ those guys usefully, and then so it was almost a no-brainer. The cerium fluoride was going to be expensive, entirely in the West, et cetera, et cetera. So he went on the limb and he chose lead tungstate, and it worked out beautifully. But they were sweating it for the following 20 years because they started growing. One of the Russian factories had 400 ovens, 400 furnaces lined up, and they started cranking them out, and they put them on the shelf and come back in a week, and they had broken. Okay, so anyway, okay, enough of that. I need to get past the second slide. But the other thing is, and I was just characterizing to David, there's sort of 3, our work is driven by sort of 3 pushes on developing better or newer scintillators. So this I'll count as the first push, and it has gone successfully into the history books. And the next one, maybe skip one, the third one also comes from this, and that's the next generation, the high luminosity LHC. So events are there, even as it is, and a way to get around that is to up the luminosity, the collisions per second by 3,000 or thereabouts. Let's see how I might, sorry, I can't figure out okay, let's try that. All right. Just hold my hand. Strike out that film. Anyway, okay, so that's certainly a way that we can get a lot better statistics on the data, but it really presses because now you have to go into where there are 3,000 collisions happening simultaneously in this small volume, and you try to use time of flight of the photons to pick those apart. So they want picosecond response of the scintillators now, or at least picosecond on the leading edge. So that's a grand challenge, and it's being worked on, including us. And then, so those are 2 of the pushes, and now I'll move on. And then there's this one. And so it didn't all jump up with 9/11, but it was already going on. So there are 2 issues here. One, which had been going on a long time, is nuclear non-proliferation, just to keep track of things all over the world and where they're moving that are nuclear, special materials, as they say. And the other one, of course, is Homeland Security, and both of those agencies are in there pushing the scintillator development, and they're both of them supporting our work. But they're sort of different things. So this would be, well, either one will use this detector, portal detector. But Homeland Security wants to do more than just detect nuclear materials. And there does exist a detector. It's called a time and position tagged neutron activation detector, which it does operate. It's not in the field, but it can give you a three-dimensional picture of the inside of that truck, labeled by every chemical element and every isotope that's in there. Anyway, it takes a long time working on it. But so there are some fantastic things being done. One that's probably going to be more useful, I think it's actually an excellent idea, and it'll come back to, I don't know if this bothers you, but so in the field I'm working, the calls for proposal literally say in the top line, and the proposal has to say cost, low cost. And the thing is, one of the best ways to get at this problem, and I think it is a problem that we need to deal with, is to make spectroscopic detectors cheap enough that you can put one on the belt of every cop, every fireman, every garbage man, and it just does GPS positioning and reports back. The cop never has to pay attention to it, but you'll get a map, a roving map of the whole country of what's out there, and these are parts of the so-called global nuclear detection architecture, which DHS is trying to do. So anyway, what's different about that? They don't need the high speed. They want the good resolution, because you're trying to get in and separate the isotopes, and they want the good, and we've already got good resolution. And if some of you will know this, you'll say, I'm in nuclear physics. I've had high purity germanium detectors forever almost. And I guess the next slide is that. What did I do? Well, that was, what? Okay. Well, it may be something I clicked on here. Let's see. Let me try these down here. Well, okay. Well, let me keep on talking with it. So it's not essential. When I do show the slide, though, it's going to show you that germanium is a really good high-resolution detector, and then it's going to compare some others that are obviously considerably worse. And basically, there are two problems. One is that germanium detectors are about $50,000 each. And that's not going to break the government, you think? I don't know, unless you try to build a project that has 68,000 of them. They still may or may not break it, but the other part of it is they have to be operated at cryogenic temperatures. So are you going to have 68,000 coolers, or probably this roving detector on the belt thing is going to be 100,000 or 250,000 of those, and you certainly don't want to be dragging the viewer around. So anyway, okay, that's good. Thank you very much. Okay, so here's the comparison. You can see on the top line there. So yes, there does exist a detector, but that's the sign of this field. We have to be able to do it cheaply, because we have to apply these things in lots of places. Sorry, get this up. And then the other reason the germanium would not have worked, say, at the LHC, is because the reason it gives you that high resolution, it's a highly perfect semiconductor, and when you immerse it in that field of heavy particles coming off, it will not be a perfect semiconductor for very long. So anyway, there are multiple reasons. So here's the, thank you. Here's that standard sodium iodide being used since 1949 and still used very widely, but you can just see, boy, that's miserable. This is and that's maybe $100 per cubic inch. And then here's one of the newer materials, lanthanum bromide. It's about $3,000 per cubic inch, and it's both of these are highly hygroscopic. Either one, set it on the shelf, it'll turn into a liquid puddle. And this one is very, very mechanically weak and sensitive, even though the oil companies put these down the oil wells to do logging of the elements and densities.
What's the difference in the widths, I'm sorry, between sodium iodide and germanium? Is that just due to one is running cryogenic temperatures and the other is just a thermal width, or is it just the resolution? I mean, the sodium iodide usually won't run that.
You know, if you
get some loading there.
no, you would not, and it's sort of a crapshoot what you would get. And we various people have run it at low temperature. It can get worse actually, but it can also do better. But they'll certainly not look like this. And this one basically is because of the perfection, and it's also and the statistic. These operate according to Poisson statistics, and these being actual charge carrier collection have different statistics, and that contributes too. But it's mainly these being such perfect materials. You produce the electron hole pairs, and you manage to collect pretty much every one of them, and that's what's not giving that non-proportionality. Whereas down here there are lots of things going on.
Just to orient myself here, the energy resolution here is not from a spectrometer, it's from just number of counts.
The crystal is a spectrometer. It just sits there, yeah. And so for the ray that comes,
N times the gap energy.
yeah, there are some number of photons per MeV is the way they do it in the field, and it'll be stated for the scintillator. But it's just an approximation. In fact, probably the next slide may even, yes, okay. And so here it is. We get the way to quantify that nicely so that we can try to work with something that's quantifiable. Is this? It's called proportionality. So finally, that word I used up front, either non-proportionality, that's the fact that these are all curving. So the ideal, the perfect detector for resolution would be just a horizontal line, because you could then say, and they're normalized out here at 662 keV, but a horizontal line would say you get that many electron hole pairs for that many EV, regardless of the number of EV you have. And some of them are coming pretty close, like the lanthanum bromide I mentioned, and the strontium iodide is even better. And so a lot of people look at that and say, well, you just record that and then calibrate it back in to remove this nonlinearity. But that doesn't work, because the stopping of a ray is stochastic. Every time is different. Every gamma ray, they can produce Compton electrons, can produce photoelectrons with Augers that follow. So it's loads of pathways to stop a gamma. And even when you've stopped it and you launch a high-energy electron, there are loads of ways for that electron path to split going down, and it splits at different energies. So you're always doing a big averaging over this energy scale. So whatever departure from a straight line you have will turn itself into an increased line width, and that's the loss of resolution. And so this was the big problem. The sponsors say, get rid of that curvature. And so Berkeley, Steve Lorenzo there undertook a good engineering brute force method. So sort of like the Russian factories, Berkeley set up not that big, but maybe 30 or 40 crystal growth ovens, and powder growth. And so they just literally grew thousands of powders from almost anything that can be composed, and then they would test them. Having the powder give you a signal does not say what the single crystal is, but it certainly, that this was going on. And that's when I got into the game. The sponsors were saying, this is good. Berkeley's doing good work, but, they're all, and this will warm your hearts, probably. It warmed mine. The sponsors themselves were saying, but wouldn't it be better if we could find out fundamentally what's limiting the resolution, and then we could use that to design things from the outset. So, and to come in then, and it still didn't make sense that a laser person would be working on this. So Bill Moses was sort of head of the effort. He and Steve were head at Berkeley, and Berkeley and Livermore had set up this Compton coincidence technique, because just making this measurement is hard. You can't, how are you going to do it? This is versus electron imaging. You can't fire the electrons in from outside because they're going to interact with the surface region in a strange way, and they're also going to charge the sample, and it's just not going to work out. But what you can do is launch electrons of known kinetic energy inside the sample by bringing in a gamma ray, which Compton scatters from a valence electron, and then you surround, so this is the gamma ray source here, you surround it with 5 of those nice germanium detectors, and you are collecting the scattered gamma rays after the Compton scattering, and you analyze that in angle and energy, and kinematically that specifies the energy of the electron that was launched from down inside the sample, and you make the sample big enough because the electron range is going to be 100 microns or something. No, 1 micron. Anyway, so that's what gives these data. It's light yield versus electron energy of that launched electron. And so Bill, this was a big deal to set that up because it's good data. But as Bill told me, he said, well, but all we get is the entire integrated result of the full stopping. That's the only thing this experiment can tell us. And how are you going to pick that apart and do physics? Is there something you can do with lasers that would help that? So, a couple of things. And so finally, I'm getting into the talk. I will end on time. But, okay, so first, what's going on in that track? And this probably from many fields you know this, and I came up through surface science for quite a while. And so I recognize this as one way of plotting the universal curve of electron mean-free path. So the mean-free path is not plotted here, but this is the EVDX, EV per nanometer. Anyway, so here's the plot. At about 100 volts, every material, I don't care what it is, has a mean-free path of about 3 angstroms. And that's how come people can do surface science. And so that's when we put in, say, the megavolt gamma ray, megavolt electron, you're down here in the rate of depositing energy, or if you like, convert that with the radius, 3 nanometers, into a density. And then when you get up here toward the track end, or specifically here, you've gone up by 2 decades in the excitation density. And that's okay, except the things we suspected, everybody suspected of causing those nonlinearities had things like dipole-dipole quenching, which is 2nd order, and Auger recombination, which is 3rd order. So you've got something 3rd order in a quantity that's changing 2 orders of magnitude, so you're going to expect the Auger recombination to possibly be changing 6 orders of magnitude in its rate. So, I mean, it's just scary numbers like that to look at. And so what Bill and I talked over was we could go in, and here's using what's probably known to you, Gent 4, standard tool. We can calculate, simulate these multiple statistical things. Here's what the electron tracks do, but that's how they do look like this sort of long spaghetti.
So this is a numerical simulation?
This is numerical. It's standard use in the high energy community. we work closely with Pacific Northwest National Lab, and Gen 4 does not handle the last 200 volts very well, because mostly they don't need to, but in this field you do. So PNNL developed their NWEgram, which takes it all the way down to phonon energies. And we, in our group, we've been doing some comparison of those two, and NWEgram is better. Okay, so anyway, that's going on, and I'm trying to make up. So this is the simple version of the transport and rate equations that we'll be looking at. It would apply in a self-activated scintillator, and that most often actually means something that has self-trapped excitons that are going to give you the light, but they don't have any foreign activator. It's just a dopant. And just to quickly say what's going on. So G is the generation term. That's what makes that, we think, a 3 nanometer cylinder. Diffusion of each carrier electrons, holes, and excitons, capital N. And then we got trapping of them, we got exciton formation, we got Auger, and then we have radiative decay of excitons and dipole quenching, for example. So that's what we would be trying to solve inside the track. And remember, these things are all written in terms of the carrier density or excitation density, and that's the thing that's varying over 2 orders of magnitude in kind of unexpected ways, anyway, in stochastic ways. And so the experiment number 1 with the laser that we did, and this is the one Bill had sort of asked for, is if we could dial up each of those densities one at a time, so kind of simulate experimentally what's going on as the electron loses energy, and measure the light yield versus excitation density. So I used, I'm sure I know we got nonlinear optical people here, so there's something called Z-scan. As normally used, you're trying to investigate the nonlinear index of refraction, so you make the sample transparent and see the effect of density as you scan this Gaussian beam through there on acting on the light. We don't do that. We absorb all of it, so it's just a way of studying dependence on excitation density. And so when we do, we get a dip in the Z-scan, so versus position, Z, and it is a accurately measured Gaussian beam, so it's nicely well controlled as we scan through. And this is for 2 well-known scintillators, bismuth germanate and strontium iodide. One's a halogen, the other's not, and it looks like they're behaving very different. Then just by putting the numbers on, so we can calculate, we know the beam profile, so we put fluence along the top, and the curve still looks the same way, but then we can plot it versus log of the fluence, and that begins to look sort of like that non-proportionality curve. It's not the same, but it's getting there. And you see these things are behaving very differently. And this, I'll see if this kind of catches your interest. It certainly caught ours. We could not understand it at first. So then the student who did this would fit it to a model of second-order quenching and third-order quenching in the spatial profile of the laser deposition, and try to fit the model to this. And you could fit one or the other, but not both. So you found that in BGO, it fit the second-order theory very well, and absolutely did not fit the third-order theory. And the conclusion was that the free electron hole, the free carrier fraction, was 0. Everything was behaving as excitons here during the quenching time, which is pretty short. But then we come over to the strontium iodide, and now it's the other way. Only the third order fits. You cannot fit a second order theory. That says nothing is excitons, everything is free carriers.
It's a function of density. You're saying all densities,
At all
electrons are all excitons.
Yeah,
It's
right.
not changing as much.
That's right. And then we could pick materials or combinations of the excitation energy and get things that went in between. So there did exist mixtures of things. But this was a lot of head scratching at first for us. It was bismuth germanate. So anyway, I've used, so let me get to the bottom. So I think it makes sense. But I mean, we really had worries about indistinguishable particles and so forth. How do you know it? Everything's at high density here. How do you know they're paired or not or whatever? Well, in this case, you know because of the way they quench each other and the kinetics. But the big difference in these is the electron-phonon scattering time, by which, remember, these hot carriers lose their energy, is here, and it depends principally on the optical phonon frequency. And cesium iodide, and the heavier the ions, the lower the optical phonon frequency, and the slower the cooling. And so cesium iodide, by calculation, is sort of the slowest. It's got a 4 picosecond cooling rate, so the electrons are hot until there, so they're not going to form excitons. This is yttrium, aluminum perovskite. Perovskites are everywhere these days. And it's mostly, this one's heavy, but it has enough light ions in there that it's got a really fast phonon cooling rate, and it's also got more complicated phonon structure, and that also accelerates the cooling rate. So these look like they're not much different, but then you see I expanded the scale 10 times, so this is like 30 times faster than that. And I won't dwell on it, but we believe that's half of the, or maybe 60% of the reason is just these, in this material it was remaining hot, and in oxides generally it's that light oxygen atom that pushes all the oxides down to the really fast cooling rate. So they cool, they do form excitons very quickly, and that's what we see interacting. The other thing going on is
all the controversy about the exciton formation time? There was like orders of magnitude debate about this.
I wanted you to catch me up on that. It's probably going to be real useful if you do that. I was up in the wide gap materials, I guess, and didn't know, but that's please do. Okay. To bring in the other thing that I mentioned, the self-trapping, because that, and I already sort of said why that's important, but just to say, in the halide material, alkali halides, but many, many other halides, and that's part of the thing. I'm still planning to write a paper on why it is that all the best scintillators, by the criterion I've given out, are halides. The oxides are crappy. And I think it has to do with, I even think I know why, that it's the presence of the self-trapped holes. And it's basically any of these halides, metal halides, the halogen picks up the metal electron and becomes xenon-like, and becomes a rare gas. And the metal ion gives up its electron and becomes rare gas-like. So it's just an ionic crystal of these hard shell rare gas atoms pressed together as tight as they can go. When you go in and excite the valence band, you made a very reactive open shell halogen. It grabs a neighbor, they relax together, and it produces these molecular orbitals that split. And so this is the famous VK absorption, for example. But the point is, it happens very fast. We're still working on, and we've written it into our future next 3 years to do a better. We're down to 1 picosecond upper limit on the self-trapping time. That's not nearly well enough determined to have the effect we think it does. It needs to be way faster than that. Anyway, that's a direction.
Is there actual motion of the atoms when this happens? You get it back?
It's actually, they do this, do that, yeah. And they just form a molecular bond. It's strong, and that's where they stick, because they're not going to move it. It's no longer a band state at that point. You localized it. And why did I dwell on it? Well, anyway, I think I don't have time to do this. But so we wound up in the laser experiment measuring. There's a band gap rule of Auger. I'll just skip over it. But from the semiconductor literature, because this is great interest to people who make light-emitting diodes, then see the very, very steep, the Auger rate goes down in a hurry as a function of band gap. And it should go on forever. So in these 6 and 8 volt materials, the Auger should be entirely negligible by 6 or 8 orders of magnitude, but it's not. They jump up. And so these were our measurements on the wide gap things that should, and these are putting those together, what exists. And just we're speculating it's something like this. A wide gap gives lots of energy to the spectator electron, but it has no more momentum than was contained in the electron hole pair in the beginning, which means you throw them way up high, but there's no way they can land on the real state unless they pick up a phonon, and that's why large gap materials have extreme temperature sensitivity of the Auger. Narrow gap materials have no problem making it go. And so what do we think is going on? The self-trapped hole localizes the hole. That means it spreads its momentum over the entire Brillouin zone. So there's plenty of momentum, we think, to cause grief, because that's what it does. But anyway, okay, so that was the so-called Z-scan part. I realize there's only like 5, maybe 10 minutes left. So we'll switching to this another use of lasers to do it, and that's kind of just straightforward pump probe absorption spectroscopy. And it's kind of a standard technique. So we need to cover from infrared as far as we can go to ultraviolet as far as we can go. So we use a OPA for the infrared through visible, and then we use supercontinuum for visible through ultraviolet. And these are the kinds of things that we want to measure, is trapping rates, exciton formation rates, and that sort of thing. So this, for example, what I've been taught, so this is the self-trapped exciton bound electron trend. The whole transition we've also measured, and it's way down in the ultraviolet. But this one here at about 0.5 eV is the electron bound to the self-trapped hole being excited up. And that's good because it's a signature that we can recognize, and we can also, as we see here, you're measuring the time for that to be formed, and it's a complicated formation. It jumps up, comes down, goes back up. I'll show you that more in a minute. Then we put in the thallium, which is in the real scintillator to make it operate at room temperature. And here's what I was talking about. It's such a good trap. This is the same spectral range. It just absolutely kills the self-trapped exciton, or prevents it, or whatever. And so that this is nothing. So basically put in thallium, they all go somewhere else. And so here's kind of, it's like knowing this. So this is why do we do this? It's because you need to know the sequence in which all of the main charge states are formed, and you need to know the quantitative capture rates and reaction rates, because I haven't gotten to the model yet. And so here's what we have done, for example, in the cesium iodide, and maybe I won't bore you with this, but this self-trapped exciton formation, so we see that here. This is something, let me not go, but we can also measure this. It's in the ultraviolet also. It's not shown here, but these are the important characters. So this is what I mentioned. You make electrons and self-trapped holes in the very beginning, and then you have these dopants in, and this dopant is bivalent, so it can capture the self-trapped hole and make a doubly charged activator, and it can capture, this is the natural state, the substitutional state for cesium. And so it can capture an electron, make this thallium 0, and that's the one here that's real. And also here we see, so what disappeared there pops up here in the visible. These two are definitely related, and we can measure the rates. And then you get the light, the thallium light that's not quenched at room temperature comes from these two, and I'll just label this as, we call this reaction 2. Self-trapped hole moves around and finds the thallium 0 and gives you light. Or the thallium 0 later releases an electron. That's how come it's slow, the sodium iodide problem. It's these late-term releases going on. And the electron finds this thing that you made and stored the hole, and then that gives you the excited state and you get the light. So those are input data for the model. And here's an interesting thing, getting back to the formation time of a self-trapped exciton, and we can, with the laser, we can't choose arbitrary starting energy, but using different harmonics, we can produce carriers that are right at the band edge, which is this case, or we can produce carriers that are 3 volts above the band edge. And they behave, these are hot carriers, and they behave differently. This dips way, way down for starters, and why is it dipping down? We believe that's impact ionization by the hot electrons that were produced. So, because from the spectrum, you make the self-trapped excitons in the very beginning, then you apparently ionize them, and then they grow back again once the carriers are thermalized. But here, I just say the analysis was done and shows not only is the formation time, this arc of the curve, about 4 picoseconds, but there's a different 4 picoseconds. For low energy electrons, the formation starts immediately. For these hot electrons, there's actually a 4 picosecond delay before anything happens, and then it starts forming. And the calculated carrier cooling time is 3.6 picoseconds. So anyway, that part seems to make sense. And then by varying the thallium concentration, we can extract the bimolecular exciton formation rate constant, and we can extract the capture of electrons on thallium rate constant. Okay, so I'm telling you all these quantitative rate constants. And so that's the last piece of this. We are winding up. And this is the simplest case, again, just to illustrate. But again, you produce something like 10 to the 20, maybe 10 to the 21 electron hole pairs per cubic centimeter here. Initially, at time 0, confined to about 3 nanometers. That's an enormous gradient. Really, they want to go out. But the self-trapping prevents the holes from doing the same thing, and so this, so here's what, our model, the transport and rate equation model calculates what we call local light yield, which is light yield as a function of excitation density. That you can't really measure, but we can calculate it. And then this is from the Gent 4. It tells you the probability of making this many electron hole pairs per cubic centimeter versus this many. Okay, and then you integrate. They're both functions of that excitation density axis. So we integrate the product of them, and it gives us the proportionality curve, light yield as a function of the, because this is calculated separately for different electron initial energies. So this is the bottom line. This is what the model calculates, and this compares directly to the gamma ray experiment. So that's where we compare all of our measurements and light yield model to the final gamma ray experiment. So I'm going to rush through the last bit on the modeling. There's that picture again. So again, don't have to show that. Oh, this is worth. And so, whoops. What did I, okay. Maybe okay, let me go here. So this is the important part to see. This is from the model where we can put in the, the model handles diffusion of hot electrons and then thermalizing and thermalized electrons as they thermalize. And so this is where I was saying the holes get deposited way down there near the core. The electrons, being hot, go way out here, and what have you done? You've immediately separated the electrons from the holes, so you've actually turned off the Auger, and you've turned off the dipole-dipole, and you've turned off the capture. You've turned off lots of things. That was not appreciated before we got into this. And then you're going to reform them later. So there's lots of complications. And so here in this little diagram, I did, so the...
Actually kind of like a...
Yeah, exactly. And it,
pulled back, so
I wound up using my hands.
and then they are wrong, but-
Actually, yeah, exactly. So in something like 4 picoseconds, they're out here, everything is turned off. Then they say, my God, what kind, a line charge has a logarithmic potential. It never ends. It's not like a point charge. It's a tremendous potential pulling them back in. They cannot escape from that line charge. So, and that's what's shown here. So the hot ones go zooming out with their characteristic hot electron diffusion coefficient. The electrons, if they still survive and are not captured, many of them are, they'll, after 4 picoseconds, now they see that electric field, and here they come, rushing back. But most of them, there are very few of these because most of them are captured on this with that really high capture rate. And so then finally these holes, self-trapped holes, can diffuse outward, but that's your microsecond. Anyway, that's your slow process. And okay, so it's that kind of thing. And now I don't need to do that. And again, this showed the picture. This is a digression. This was excellent scintillator in terms of proportionality. This is pretty much lousy. And we wondered, what's the difference? They're both halides. They're both similar masses. They both involve iodine. But this is much better. How come? So I had a student, a theoretical student, doing calculating the group velocity. This is a this is a 2-atom unit cell, so it's got very simple bands. This is a 24-atom unit cell, large unit cell, very complicated dispersion bands, but mostly very flat dispersion bands. So the group velocity is very low in this material. So out of time, but there's a very good Russian theorist who summarized it very well. And he said, you want poor hot electron transport and good thermal electron transport. That means they don't get very far out because you don't want to cast them way out. But then when they thermalize, they can surely well come back in. So that's this one. Okay, we'll have time to discuss, because this is right, sort of at the end, but it's also what we're doing right now, 2015, and then one that we just did in 2017 on this. And this is realistic modeling. There are various models out there, and a lot of other groups will say, do say sometimes, my God, what have you got 27 parameters in this model. What are you going to do with that? And they'll say, well, we've whittled it down to 3 parameters. That's much, much better. Well, let's think about that. Is it? Because what we want to do with this, and this is strongly top line of our funding now, is to produce an engineering model, something that you can investigate things on the computer before you do them. If you've simplified it so much that you don't contain some of these things, there's no way, they're not in your model. You can't deal with them. So better to have them in than not to have them in. The other way that I didn't leave time to do, but I may zip down the line, I would invite you to go through this list and tell me which ones don't matter. You know, so with the generation, spatial generation in time, no, that's diffusion, electric field transport, we know that's capture, exton formation, Auger quenching, go down through the thing. There aren't any weak parameters in there. I mean, if they were weak, we did leave them out. Okay, so where do we, so here we did. We got the same material at changing temperature and putting in the dopant. And then we got the model, the same model, with one set of parameters, many of them, in fact, coming from independent experiments. Okay, pretty good agreement. So we think we're on the right track. We're not totally satisfied because we were modeling a pretty non-featured curve there, this kind of thing, and we're doing it with 27 parameters. Not all adjustable, but there are like 2 of them and 2 or 3 that are adjustable. So not real satisfactory, and we realized I mean, there's a better way to do it. And so then the following paper we find out, okay, but you don't have just that experiment. There's loads of experiments of different kinds on these materials. So the whole thing of the pulse shape, the components to it, anyway, I won't go. So there are 3 separate components, and there's nailed down what the actual Thalem lifetime is. So we have to deal with the matrix to make that up. This is the one that was really important, and it's next to the end, I think. So in 2014, there was a very good group from Poland that for the first time ever measured the proportionality curve for each of those 3 decay components that I showed on this slide. And enthusiastically received it. We'd never seen that before. That's incredible. But what does it mean? Can you fit it? And I was sitting there saying, I bet we can fit that. And not just fit with variable parameters. So here's our model, as I showed you, with any mostly measured parameters, any last ones, we spent getting the decay times right, and then we froze them, and we didn't change anything, and we said, will the model just straight out, predict this behavior? And I'm claiming it does, plenty good. So we think that was a good behavior, and I'll leave it, and the model can show us all these radial dependencies, but I'll leave that. And so this is the students, and so this is my research professor. You probably met him, Barak. This is postdoc Sergey, and 3 graduate students. And I will speak up. So we have these 2 funding things. I'm kind of proud of this one because this venture NNSA put all of their national lab funding in one basket called a venture. So there's one actual multi-party research group, and we have face-to-face quarterly meetings of the PIs. That means I'm always going to the West Coast. But I'm proud of the group. So it's Lawrence, Berkeley, Los Alamos, Argonne, Pacific Northwest, Sandia, New Berkeley, Minnesota, and Wake Forest. I just bragged a little bit. And the other one is from DHS. So that's that. I left 2 seconds. No. Thank you.
So with these simulator detectors, is it only the rise time that matters? The fall time doesn't matter so much?
No, the fall time, I would say, matters first and foremost, because if the previous pulse is still falling when your next pulse gets there, you can't do anything with it. And so the rise time is becoming very important. Like I said, in that LHC upgrade, nobody currently thinks that you're going to get a scintillator that will decay in a picosecond, and that's kind of squarely in you guys' area. But I've worked on that too, the idea of giant oscillator strength of exciton emission and so forth. But there's a fundamental, Fermi's golden rule gets in your way because, in fact, I had a student do this. I said, go to the NIST tables and find me the fastest atomic spontaneous. Scintillation is spontaneous emission. And find me the fastest atomic spontaneous emission that exists. And it was 7 nanoseconds for a beryllium charge state. What's going on? You guys know faster things than that, and I do too. And like we know that dyes have 2 nanosecond, maybe 1 nanosecond decay. That's because the dye delocalizes the electron to a spatially much larger initial and final states. And so when you do that golden rule interval, you get the higher rate. But for an atom, you're stuck with something very small. And then, sorry, you got me. But then this thing of giant oscillator strength, in principle, comes in. So if you delocalize over many oscillators, as long as they're coherent, the oscillator strength goes way up because they're coherent. So it's like a plane wave, or like your in antennas. All the antennas emitting in phase, and you'll get much higher power, much higher rate. So, okay, that was nice. But back to the actual thing, and maybe that can be made use of, but it's also possible to use the rising edge of a slower, you'd like it pretty fast still, but the rising edge to give you the triggering you need to pick these things apart. And so there, my student and then postdoc has worked with Paul Lecoq, and he went to his next postdoc working on the quantum dots. And so they have actually done experiments now to take a more standard scintillator crystal, which is going to stop the gamma ray and give you the total energy readout, but you coat the front face with a thin layer of the quantum dots, and you use their very rapid emission to give the trigger.
Yeah, so I just want to, so you have this charge tube, and then there's, of course, there's a lot of, I'm not a solid state physicist, so I'm not part of it. So what's happening is all of the stuff is happening within a tube of what diameter? What did you say?
It's initially 3 nanometers, we think. That's the weakest number in all of this, but it comes from indirect reasoning. One of them, I think maybe the best one, came from me, which was we measured the nonlinear quenching rate and then said, let's see, it's coming to me slowly here, but essentially saying what density will it take to produce that rate using some extra information on what the rate should be, and that shrunk it down to about 3 nanometers. But we need to do better than that, and we think, well, it'd be a long answer, but
Pictures the gamma ray shoots through, and it's got a tube surrounding its path.
a tube initially very small because it's just a succession of single location depositions, and you kind of connect like what Gent4 does. You get your linear deposition, DEDX, connecting that, but it's saying that you don't make your carriers initially way out there, but they surely don't stay there very long at all. So they've all, and our model plots that out. Take the hot electron diffusion coefficient, and you're already moving out in much less than 1 picosecond. So it's starting to expand, but you have to start somewhere because that's what drives the expansion. But it very quickly goes out. So the stopping place is usually, it depends on, but for cesium iodide it's about 50 nanometers. And that's the stopping of the hot electrons. But most stuff comes back. And so, so then there's the slow diffusion. You think that could go a lot more, and it does some. So our model again shows things going out 200, 300 nanometers finally, but most of them, the bulk of them, are coming back where the holes were.
So is the right model to think of the gamma ray shooting along and it's red shifting as it goes, as it loses energy, all these electrons?
Well, it's not the gamma. The gamma ray events are instantaneous in one location, and then if it's Compton, a scattered gamma ray goes off and does it again and does it again.
Okay, so it's not one gamma ray, but it's a succession of gamma rays.
A section derived from the first one, and what they're doing is launching these electron tracks, and then it's the electron track that's giving you the light.
And this path you showed, it's not in a straight line.
Yeah, they're doing this, and then they'll make what's called a delta ray. They'll branch off. A high energy electron is produced by collision, and that's what makes the problem tricky, because you get that randomly.
So there's there's also a rate issue of, if you have a bunch of particles coming at a high rate, but they're distributed over a big section of the simulator, there's another problem of having a really pencil beam that's going through one section, and all of these regions that, if they start to overlap in time, then there must be a nonlinearity associated with the density of the flux of incoming tracks compared to if you have this track that's being distributed over time.
I may not understand it correctly, but you don't get, practically speaking, you don't get overlapping of separate tracks. And why do I feel I can say that? Because the tracks themselves are sort of at most a few hundred microns long, and then this may be 50 or 100 nanometers wide, and the number of gamma rays that intersect any reasonable detector per second it's a finite number, like at most 1 million. But there's the chance that even with 1 million events that you're going to have overlap it turns out to be small. Yeah. But the other issue is to be sure with these multiple gamma rays that you catch them all, and you don't always. But that's how come they calculate the size of the crystal they need. That most of them you'll catch them.
Again, also just looking at myself, in these beam experiments, how long was the collision time? Like, how long are these things on for? Is it some milliseconds, or is the beam continuous, or is it pulse?
It depends on, in the high energy experiment, the crossings, so these counter-circulating things, and that's what's 10 to the 8 per second. And so,
How long is that crossing going on?
well, the speed of light for this, so it's not very long. And in the past use at LHC, there was on the average only one event, only one collision, not event, but one collision per crossing. And so that's really, that's a, well, anyway, it's 10 to the 8 plus multiple gamma rays. So, but then 68,000 detectors to average over. So I think my point is still remains, but to answer your question, it's a high, yeah, maybe something like 1,000 gamma rays per collision would not be unusual, probably. I'm totally guessing. And so that's a lot. That's 10 to the 11
So
gamma rays.
involving within a collision. They're basically saying, for a given collision, how many total?
No, they're asking for a scintillator fast enough that it can recover in 10 nanoseconds and be ready for the next one, because those are precious events. You don't want to throw them away.
Okay, we do want the timing resolution on the second.
Yeah.
And that's why, like I said, the rise time, that's what, that helps the timing.
Well, because what they want to do is pick out from the rise time and actually where in this, I probably was too short, in this bunch with up to 3,000 collisions going on, and I don't see how they can expect to do 3,000, but, you know, and maybe they don't either, but start simple with, let's say, 20 collisions, and then from the time of flight, yeah, you say, well, that was in the back of the pack, and this was in the middle of the pack, and this was up here, and try to pick them apart.
Okay,
Well, thank you. Mhm.
So we'll go down to blank, empty flash drive.
Just a quick question also about the, I mean, is anyone you know that's still like doing this kind of work for like the liquid scintillator or, you know, water soluble, because that's sort of what we're.
Yeah,
Okay.
so